Hello and welcome to today's presentation on thermochemistry. This is for Rockville High School Chemistry Distance Learning, Session 3, the week of 420 to 426. A couple of key terms and equations I want to go over quickly today before we start our presentation are heat, given the symbol Q, enthalpy, also given the symbol Q, thermochemistry, endothermic processes, exothermic processes, calories, joules, heat capacity, specific heat, and lastly, the specific heat equation. These are the terms and equations that we will cover in this presentation. These are the learning objectives for this presentation. The big ideas are conservation of energy, which says that in all chemical equations, all chemical reactions, I should say, no energy is lost or gained. And the other one really relates to heat flow. And basically, hot things transfer energy to cold things. All right, here's our agenda for the week. We have some YouTube videos that we'll watch or you can just view the Google slide presentations, and they'll be in 3 parts. And we have some questions for you to answer, thermochemistry practice problems that will be on a Google form. There will also be a section review, which will just be practice questions like the previous one, also on a Google form. For the section review, the answers are provided. Lastly, we're going to give you an exit card. What's due this week? Well, if you go to Google Classroom, you'll see the assignments that will be posted shortly. There'll be the practice problems, as well as the exit card. Let me go back for a moment here. And there'll also be this section review and some supplemental materials that you can view on Google Classroom. All right, let's see now. The first idea we want to talk about are heat flow scenarios. If you kind of think about it, let's think about a hot cup of coffee. You order that hot cup of coffee, and at some point, it becomes cool enough for you to drink. It takes a little bit of time for that coffee to cool off. It doesn't happen immediately. Another idea we can think about might be like, some French fries that you get at a takeout restaurant. If you bring them home, by the time you get home, they're cold and soggy. And so that begs the question, why do some things cool off faster than other things? That's what we want to talk about in this presentation. Let's define a couple of terms here. Number one, energy. Energy exists in 2 forms, work and heat, and it's represented by the symbol E. The units for energy are joules or calories. 1 calorie is equal to 4.18 joules. We can understand the idea of energy as it relates to temperature by saying that it's proportional. Well, what does that mean? It means that low average kinetic energies correspond to low temperatures, and high average kinetic energies correspond to high temperatures. Heat is not exactly temperature, but it's related. Heat is energy transferred from one object to another due to a temperature difference, and it's represented by the symbol Q. Temperature, on the other hand, is a measure of average kinetic energy, and it has different units depending on what scales we're using, the Celsius, Kelvin, and Fahrenheit scales. Thermochemistry. Well, thermochemistry is the study of energy changes that occur during chemical reactions or phase changes. Phase changes are like melting, boiling, freezing. Enthalpy is heat content in a system. Technically speaking, it's at a constant pressure. We don't really need to worry about that today. For our purposes, we're going to say that heat is a change in enthalpy, and we can describe it with that mathematical equation, Q equals delta H. And if we think about 2 different objects, one hot, the red object here, and one cold, the blue object, when they become in contact, heat will flow from the hot to the cold object. And that heat flow will stop once they reach the same temperature. That's kind of the 0th law of thermodynamics, which says that heat always flows from a warmer object to a cooler object. And these are the two examples that we're looking at here. Example 1, the objects are in different temperatures. Examples 2, they're at the same temperature, and they're what's called in thermodynamic equilibrium. If you notice, the arrow here is pointing from the hot to the cold, but when they're at the same temperature, the arrows are pointing in both directions. That's showing us thermodynamic equilibrium. The first law of thermodynamics says that no energy is created or destroyed in a chemical reaction. And that's what these two diagrams are showing. Mathematically, we can describe it by saying the change in energy of the universe is equal to the change in energy of the system plus the change in energy of the surroundings, and that is always equal to 0. We will define universe, system, and surroundings in a minute, but the three people passing the hot potato around are basically showing you that the size of the potato is not changing. We're only transferring it from one person to another. So let's define system and surroundings and universe. The system, well, that's the part of the universe being studied. Systems can be open or closed. In an open system, matter can move freely in and out of the system. Think of a coffee cup again. If you leave that coffee cup on your table for a couple of weeks, all of the water and coffee are gone. That's because the system was open. But if you close a container, no matter can get in or out. Only energy can flow, and that's a closed system. What are the surroundings? Well, the surroundings are things in the immediate vicinity of the system. Endothermic processes. We've talked about this before, but let's review. In endothermic processes, the system gains heat and the surroundings cool down. And that's what this diagram is showing us. In an endothermic process, the system absorbs heat from the surroundings. Heat or energy is written as a reactant side, it's written on the reactant side of a chemical equation. And the system has a positive Q or positive delta H values. And we've looked at these energy diagrams in the past. This is to remind us what they look like for endothermic processes. So an endothermic versus an exothermic process. The one on top, the reaction, is an endothermic process, and that's photosynthesis. It requires energy to proceed. And the one on the bottom, respiration, is an exothermic process. Notice where energy is on the top equation and where it is on the bottom equation. Let's look at exothermic reactions now. In an exothermic process, the system loses heat and the surroundings become warmer. And like in our diagram, the system releases heat to the surroundings. Heat and energy are written on the product side of a chemical equation. And the system has a negative Q or delta H. And this is what an energy diagram would look like for an exothermic reaction. Now, specific heat, let's talk about that for a moment. Specific heat, that is the amount of heat it takes to raise the temperature of 1 gram of substance by 1 degree Celsius. And it's represented by the symbol C sub P and has the units of joules per gram per degree Celsius. And it's constant for a given substance. You'll often hear the terms specific heat and heat capacity and specific heat capacity used interchangeably often. They mean very much the same thing. Specific heat is specific to 1 gram of substance. And those values are often listed in tables and help you identify a substance based on its specific heat. We can also mathematically calculate heat capacity or specific heat from the equation Q divided by M divided by delta T, which is the heat divided by the mass divided by the change in temperature. And we'll talk more about that later. But it's enough to say that different substances have different values of specific heats, which means they require different amounts of energy to raise or lower their temperature. Heat capacity. Heat capacity is the amount of energy required to increase the temperature of an object 1 degree Celsius, and it has the units of joule per degree Celsius. Notice there's no mass component in there. There's no gram unit in there. Heat capacity is therefore dependent on the mass and the intrinsic properties of the object itself. For example, water has a high heat capacity, whereas metals tend to have lower heat capacities. So 1 gram of water would take more energy to heat up than 1 gram of iron. And water is commonly used as a coolant because of its high heat capacity. The picture that you're looking at there is a nuclear reactor. And most nuclear reactors have to be near large bodies of water because the reactors need a lot of water to capture some of the heat that's produced in the nuclear reaction. Let's look at the mathematical equation for heat capacity. Well, specific heat can be used to calculate the heat of a system when a substance cools down or warms up using this equation. Q equals mCp delta T, where Q is the heat, M is the mass, C sub P is the heat capacity, and delta T is the change in temperature. Okay, that's enough about heat capacity. Let's talk about heat transfer for a couple of slides here. There are 3 basic ways that hot things transfer their energy to colder things: radiation, convection, and conduction. Conduction is the transfer through direct contact between objects. Radiation is the transfer of heat as electromagnetic waves through a vacuum and/or through matter. Convection is transfer of heat through the movement of fluid matter. Let's take a couple of slides and talk about these 3 forms of heat transfer. Conduction occurs through direct contact. Temperature of an object corresponds to the average kinetic energy of moving energy of an object. And when particles bump into each other, the warmer particles transfer some of their kinetic energy to neighboring colder particles. And at thermodynamic equilibrium, particles will have roughly the same amount of kinetic energy and heat flow stops. Conduction is the most efficient mode of heat transfer. The next one I want to talk about is radiation. Electromagnetic waves travel through matter and space. When objects absorb radiation, it's transformed into heat. A great example of electromagnetic radiation are microwaves. When you put food into a microwave oven, it gets hot because that food absorbs that electromagnetic radiation. Another classic form of radiation are nuclear reactions produced by the sun, which give us our sunlight. Solar radiation travels through outer space and is absorbed by Earth, most of that absorption from oceans. And lastly, we have convection. Convection are when fluids, which could be a gas or liquid, are heated, the particles move more vigorously or more quickly, sliding past each other and move farther apart. In doing so, they become less dense because density decreases as temperature increases. Convective currents, warmer, less dense fluid rise to the top, and cooler, more dense fluids sink to the bottom. That's what's happening in your pot of water that you boil to make pasta. Interestingly, that's also what's happening at the center of the Earth and through the ocean currents and all the wind currents in our weather patterns are all responsible for or are all determined by convective currents. So in summary, this is what we're going to do this week. There are going to be 2 assignments: thermochemistry practice problems, where you can check your answers, and a thermochemistry exit card. This slide says it's going to be graded, but just prior to this slide, we were told that it's going to be a pass-fail grading system. There'll also be other stuff on Google Classroom, so please look for those and email me with any questions. I look forward to talking to you. Take care.